Hello everyone, welcome to Basic Electronics Tutorials. In this video, I am going to discuss on the construction and characteristics of junction field effect transistor, in short JFET. Before I begin the discussion on the junction field effect transistor, let me give you a very brief introduction to a field effect transistor. A field effect transistor, or in short a FET, is a three-terminal semiconductor device. The terminals of the device are source, drain and gate. A FET is a unipolar device. That is, the current in the device is due to only one type of charge carriers, either electrons or holes. It is called as a field effect transistor because the current flow in the device is controlled by the electric field or potential applied by an external voltage source. Hence, a FET is also referred to as a voltage controlled device. The current across the device is controlled by the voltage applied to the gate terminal. Hence, the gate terminal is referred to as the control terminal of the device. Depending upon the type of the channel, FETs are broadly categorized into N channel and P channel devices. In this video, I will discuss the construction and characteristics of a N-channel junction field effect transistor, in short JFET. The figure 1 shown here indicates the construction of an N-channel JFET. Note that the major portion of the device structure is made up of the N-type semiconductor material. This N-type region forms the channel. Further, note that the channel becomes narrow between the inserted or embedded regions of the P-type semiconductor material. The top of the N-type channel is connected through an ohmic contact to a terminal called drain, whereas the lower end of the same material is connected through an ohmic contact to a terminal called source. The two P-type materials are connected together or shorted and are then connected through an ohmic contact to the gate terminal. So, we understand that the drain and source are connected to the two ends of the N-type channel and the gate is connected to the two layers of P-type semiconductor material. Let us recall that when a N-type semiconductor material is connected to a P-type semiconductor material, a PN junction is created. Coming back to the JFET structure in figure 1, note that the gate material is made up of the P-type semiconductor, whereas the channel is made up of the N-type semiconductor. Therefore, we can now derive the same principle that creates a diode. That is, when a N-type semiconductor and P-type semiconductor are connected together, a PN junction is created. And at the region of vicinity of the contact, as we know, a depletion layer is also created. So, by carefully observing the structure of the JFET, we note that when no voltages are applied, JFET exhibits two PN junctions. The first one is between the left P-type gate material and the N-type channel. The second one is between the right P-type gate material and once again the N-type channel. This also results in the creation of two depletion regions, which is very similar to that in a diode. These depletion regions are shown here with grey colored regions. You should note that a depletion region is void of any free charge carriers and therefore does not support conduction of charge carriers. To understand the control mechanism of a JFET, let us consider the simple water analogy shown in figure 2 here. The source of the water pressure is attributed to the voltage applied between the drain and source terminals, which establishes a flow of water, which in case of JFET is electrons, from the source, which is the spigot in the diagram here. The gate terminal controls the flow of water to the drain through the use of an applied potential, which forms the gate voltage. The drain and source terminals are at the opposite ends of the N channel, and therefore, they are shown here at opposite ends of the source and destination of the water flow. Please note, the flow of water is enabled by the application of drain to source voltage VDS, and the water flow itself is controlled by the application of the gate to source voltage, which is VGS. Here, water indicates the flow of charge carriers, which in this case is electrons. Let us now continue and analyze the behavior of the JFET when voltages are applied across its terminals. For the first case, let us consider the scenario where the gate to source voltage is assumed to be 0 volt, whereas the drain to source voltage VDS is assumed to be some positive value. The connection for this configuration is as shown in figure 3 here. Please note, the gate to source voltage for this configuration is 0 and the drain to source voltage is assumed to be a positive value. You should note that when the gate to source voltage is said to be 0, the gate and source are simply connected to each other, or in simple words, they are shorted. This type of voltage application will cause the gate and source terminals to be at the same potential, and therefore, the depletion region at the lower end of each P region remains very similar to the condition when no voltages are applied to the device. I am going to repeat. Please note, when VGS is equal to 0 volt, the depletion region at the lower end of the device remains as if when no voltage is applied to the device. On the contrary, the moment a VDD or VDS is applied, the electrons in the N-type channel at the top of the channel are drawn towards the drain terminal, creating a drain current ID whose direction is opposite to the flow of electrons, which is indicated here. By carefully observing the path between the drain and source terminals, we will note that the drain and source currents are one and the same. That is, ID is equal to IS. Under this condition, the flow of charge carriers from source to drain is relatively unrestricted and is limited only by the resistance of the N channel between the drain and the source. Let us now discuss why the shape of the depletion region at the top of the channel is bulkier than at the bottom. To understand the reason behind the change in the width of the depletion region, let us use the JFET structure shown in figure 4 here. Let us for time being assume that the N channel offers a uniform resistance. With such an assumption, we can now break down the resistance across the channel into different divisions as shown in the figure 4. We can see we have shown resistors at regular intervals of time. Let us assume that the voltage applied across the drain to source terminals is equal to 2 volt. That is, VDS is equal to 2 volt. So, the drain which is at the top is now at plus 2 volt potential, whereas the source which is connected to ground will be at 0 volt potential. As we move along the channel from the drain terminal which is at the top towards the source terminal which is at the bottom, the potential decreases from plus 2 volt to 0 volt. You can see the potential reducing from plus 2 volt to 0 volt at regular intervals as shown at the different intervals here. It should be noted that the potential at the top half of the JFET structure is higher, whereas in the bottom half it is lower. Let us recall the condition where a diode is reverse biased. That is, the P type of semiconductor material is connected to the negative terminal of the supply and N type of semiconductor material is connected to the positive terminal of the supply. Under this condition, a depletion layer is developed and it is shown here at the middle of N and P regions. If I now increase the input applied voltage, let us say VA, then as per the principle, the width of the depletion region will continue to increase. This is a very important concept, and now let us apply this concept to understand the variation in the shape of the depletion region in the JFET. Since the voltage at the top of the channel is 1.5 volt, the upper region of the P-type gate material will be reverse biased by 1.5 volt, whereas the lower region is reverse biased by 0.5 volt. Since this voltage reverse biases the PN junction, the depletion region width increases at regions with higher reverse voltage, which is at the top, and vice versa. It is due to this reason that the width of the depletion region is wider at the top of the channel than at the bottom. Please note, we have currently assumed the gate voltage to be 0. Therefore, the gate current is said to be 0 amperes. So, coming back to the JFET structure, we have now understood that the depletion region width is quite wider at the top because the potential difference between the N-type channel and the P-type gate at the top is higher than compared to the lower part of the JFET structure. Now, if the voltage VDS is increased, let us say from 0 volt to a few volts, which is towards the positive, the current in the channel will also increase as per the Ohm's law, which is V equals I into R. Please note, we have assumed the channel resistance R to be constant. Therefore, if you increase the value of VDS, then the current ID will also increase. The plot of ID versus VDS is shown in figure 5 here, and this is, please note, for the condition when VGS is 0 volt. Let us now understand this graph of ID versus VDS first. Please note that the curve is considerably straight at lower values of VDS. That is, between 0 and VP, you can see the curve is almost like a straight line. This relative straightness of the plot indicates that for lower values of the drain to source voltage VDS, the resistance offered by the channel is essentially constant. That is why this region is indicated with an N channel resistance. It should be noted, since the channel resistance is constant, the rise of current is almost linear. If we now continue to increase the value of the drain to source voltage, which is the x-axis here, until it reaches a level referred to as the pinch off voltage, which is represented here by Vp, then the depletion regions will further widen until the channel width reduces to a very small value. This is indicated in figure 6 here. Please note, here we have increased the value of VDS to a large value, and when the VDS reaches a voltage equal to Vp, the depletion regions will widen until the channel width almost reduces to a very small value. Under this condition, that is when the channel width decreases, the channel offers a high resistance to the flow of charge carriers. Now, if I apply the same equation, which is V equals to I into R, we have to now consider the variation in R. Please note, the value of R is now increasing. It is because of this reason that the characteristic graph creates a curve near the vicinity of the pinch off voltage Vp. Higher the resistance offered, flatter will be the curve of this characteristic graph. If the value of VDS is further increased to a level where the two depletion regions appear to touch each other as in figure 6 here, then a condition called as pinch off will be resulted. The value of the drain to source voltage VDS at which this condition is created is referred to as the pinch off voltage, and it is denoted by Vp. When the pinch off voltage is reached, a very small channel still exists and charge carriers still flow from source to drain. However, the current density under this condition is considerably very high. Under this condition, the drain current ID reaches a saturation level denoted by IDSS. Coming back to the ID versus VDSS graph, note that for values of the drain to source voltage VDS greater than Vp, which is towards the right side of this discontinuous line, the drain current is almost constant and is equal to IDSS. It should be noted that the drain current becomes constant once VDS reaches Vp, and for any further increase in the values of the drain to source voltage VDS, the drain current is equal to IDSS. Therefore, we can say that once the drain to source voltage becomes greater than the pinch off voltage, the JFET behaves like a current source. As you can see here, under this condition, the drain current ID is fixed and is equal to IDSS. However, the drain to source voltage VDS is determined by the applied load value. Therefore, we can say that the drain saturation current IDSS is the maximum drain current for a JFET and is defined for the condition where VGS is equal to 0 volt and the value of the drain to source voltage is greater than the pinch off voltage value, which is Vp. This is the behavior of the JFET when VGS is equal to 0, but VDS is a positive value. Let us now consider the behavior of the JFET when VGS is less than 0 volt. As already discussed, the gate to source voltage is the controlling voltage of the JFET. Please recall the output characteristics of a BJT, which are a set of curves of IC versus VCE for a fixed value of IB. In a very similar fashion, we can plot a set of characteristic curves which are a plot of ID versus VDS, which are plotted for a fixed value of the gate to source voltage VGS. Let us now assume that the controlling voltage, which is the gate to source voltage, is made more and more negative from its initial value of 0 volt. In simple words, let the gate terminal be set to a lower potential compared to the source terminal. Coming to the figure 7 that is indicated here, let a negative voltage of minus 1 volt be applied across the gate and source terminals, and let the value of the drain to source voltage be greater than 0 volt, which indicates it is a positive value. Note that the gate is made up of p-type semiconductor material. Therefore, applying a negative voltage to the gate terminal will reverse bias the gate to channel PN junction. Therefore, the depletion region between the gate and channel will widen throughout the channel in a very similar fashion as what we discussed when VGS was 0. That is, the upper part of the depletion region will widen more compared to the lower part of the region. If I now apply a positive drain to source voltage as discussed previously, then once again the depletion regions will widen near the top of the device, just like we previously discussed under the case of VGS equal to 0 volt. However, the only difference between the previous case, that is when VGS was 0, and the current case is we have currently applied a VGS of minus 1 volt. So, even before VDS was applied, the PN junction across the gate and channel is already reverse passed. Therefore, the depletion regions have started to widen even before the drain to source voltage is applied. Now, if I apply a positive value of drain to source voltage, the same process of depletion regions becoming more and more wider at the top will once again be repeated. However, the difference between the previous case and this case is that the value of the drain to source voltage required to ensure the two depletion regions touch each other, which is the condition VDS equal to VP, will be considerably low. In simple words, the value of the drain to source voltage required to reach the pinch off region when the gate to source voltage is negative is lesser than the case when gate to source voltage is 0. Therefore, we can now say that applying a negative voltage to the gate terminal will cause the JFET to reach the saturation at a lower value of the drain to source voltage, which in this case is shown for VGS equal to -1 volt. Figure 8 here indicates the N channel JFET characteristics for different values of VGS. You can see that we have shown VGS equal to 0 volt, -1 volt, -2 volt and continuing in this fashion till -4 volt. It should be noted that as the value of the gate to source voltage is reduced, the value of the drain saturation current also reduces. Please note that the pinch off voltage reduces in a parabolic fashion as the gate to source voltage becomes more and more negative. If I now decrease the value of VGS to such a point where VGS becomes equal to minus of VP, then the device will enter saturation even when the drain current is 0. That is, for VGS equal to minus VP condition, the drain current becomes 0 amperes. When the drain current becomes 0, the device is said to be completely turned off. So, we can say that the value of VGS that results in ID equal to 0 is defined as VGS equal to VP. When VP is negative, it is applicable for N channel devices, and when VP is positive, it is applicable to P channel devices. Coming to the characteristic graph itself, the region towards the right of the pinch off point, which is right here, is typically employed in linear amplifiers and is commonly referred to as the saturation region, also called as the constant current region or the linear amplification region. On the other hand, the region towards the left of the pinch off point is referred to as the ohmic region or the voltage controlled resistance region. In the ohmic region, the JFET can be used as a variable resistor whose resistance is controlled by the value of applied gate to source voltage. Please note, the slope of the curve for values of VDS greater than VP change as with the value of VGS. For example, if you consider the case where VGS is 0, the slope of the characteristic curve is quite high. For VGS equal to -1 volt, the slope has now reduced. For VGS equal to -2 volt, the slope has once again further reduced. So, we can say that as the value of gate to source voltage becomes more and more negative, the slope of each curve becomes more and more flatter because of the increasing value of the resistance across the channel. If you want to estimate the resistance offered at a finite value of VGS and VP, then equation 1 shown here will give you a very good approximation. Here, RD is the resistance offered by the channel at a particular level of gate to source voltage, and R0 is the resistance at VGS equal to 0 volt. Further, VGS represents the gate to source voltage and VP represents the pinch off voltage. Consider the case of an N channel JFET where R0 is equal to 10 kilo ohms. That is, the resistance offered by the channel when VGS equals to 0 is 10 kilo ohms and the value of the pinch off voltage is considered as minus 6 volt. If we are now asked to find the value of the resistance offered by the channel, let us say for VGS equal to minus 3 volt, then I have to simply substitute R naught as 10 kilo ohms in the numerator. Coming to the denominator, VGS has to be minus 3 volt as what we have discussed here, and the pinch off voltage of the JFET is constant and is equal to 6 volt. So, the resistance offered by the channel is 40 kilo ohms. This is how you can estimate the resistance offered by the channel and the different values of the gate to source voltage VGS. Well, with that we have come to the end of this discussion where we discuss the construction and characteristics of a N-channel junction field effect transistor. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more tutorials on basic electronics. Thank you for watching. Have a good day.